Hello, science enthusiasts, and welcome back to the channel. Today, we're diving into a topic that sounds like it's ripped straight from a science fiction thriller, but is in fact one of the most urgent realities of our time. Imagine a world without one of modern medicine's greatest pillars. A world where a simple paper cut could lead to a life-threatening infection, where routine surgery like a hip replacement or a C-section becomes a high-stakes gamble, where diseases we've considered conquered for decades, like pneumonia or urinary tract infections, once again become deadly. This isn't a dystopian future. It's a past we escaped and a future we are dangerously close to re-entering. This is the world of the post-antibiotic era, and the harbingers of this era have a name: superbugs. So, what exactly a superbug? It's a common misconception that they are a new, monstrous type of bacteria. The truth is far more subtle and alarming. A superbug is any bacterium, fungus, parasite, or virus that has evolved to become resistant to the drugs designed to kill it. The official term is antimicrobial resistance, or AMR. These aren't alien invaders. They are familiar foes, like or that have learned our playbook. They've developed sophisticated defense mechanisms, turning our miracle cures into nothing more than sugar pills. But how do they do it? How does a simple microbe outsmart our most brilliant scientists? It happens through the fundamental engine of life itself, evolution, but on hyperspeed. There are two primary ways bacteria achieve this. First, through simple random mutation. Every time a bacterium divides, which can be as often as every 20 minutes, there's a tiny chance of a copying error in its DNA. By sheer luck, one of these mutations might, for example, alter the shape of the protein that an antibiotic targets. When you introduce an antibiotic, it wipes out all the susceptible bacteria, but this one lucky mutated bacterium survives. With no competition, it multiplies, and soon you have a whole population of resistant bacteria. The second method is even more sinister, and is what makes this crisis accelerate so rapidly. It's called horizontal gene transfer. Bacteria are incredibly social. They can pass genetic information directly to each other, even between different species. Think of it like a microbial internet where they trade survival cheat codes. They do this in a few ways. Through a process called conjugation, where they form a small bridge and pass a piece of DNA called a plasmid. Through transformation, where they absorb stray DNA from their environment. And through transduction, where a virus accidentally carries a resistance gene from one bacterium to another. This means a single resistance gene can spread through a bacterial community like wildfire, creating multi-drug resistant strains, the true superbugs that can fend off several different types of antibiotics at once. To understand the gravity of this, we need to rewind the clock. Before 1928, the world was a very different place. Bacterial infections were a leading cause of death. Then, Alexander Fleming famously discovered penicillin. It was a revolution. This kicked off the golden age of antibiotics from the 1940s to the 1960s, where dozens of new classes of antibiotics were discovered. Humanity finally had a shield against its oldest microscopic enemies. Modern medicine as we know it, from complex cancer chemotherapy, which weakens the immune system, to organ transplants that require immunosuppressant drugs, is all built on the foundation of effective antibiotics to prevent and treat infections. But we became complacent. We overused and misused these precious medicines in humans and agriculture, creating the perfect evolutionary pressure for resistance to emerge. And just as the threat was growing, our pipeline of new drugs ran dry. Why? The low-hanging fruit has been picked. Finding new compounds that are lethal to bacteria but safe for human cells is incredibly difficult. But the bigger problem is economic. Developing a new drug can cost over $1 billion and take more than a decade. For a pharmaceutical company, a drug for a chronic condition like diabetes or high blood pressure, which a patient takes for life, is far more profitable than an antibiotic that a patient takes for just 10 days. Worse, to preserve the effectiveness of a new antibiotic, doctors would use it as a last resort, limiting sales even further. The market is fundamentally broken. The consequences are already here. The World Health Organization calls AMR one of the top 10 global public health threats facing humanity. Already, resistant infections are estimated to cause over 1.2 million deaths per year, and that number is projected to soar to a staggering 10 million deaths annually by 2050 if we don't act. That's more than currently die from cancer. We're talking about superbugs like MRSA, which can turn a simple skin infection into a flesh-eating nightmare, or CRE, which are resistant to nearly all last resort antibiotics and have mortality rates as high as 50%. So, the threat is real, the challenge is immense, and our old weapons are failing. It's a grim picture. But is it a hopeless fight? Absolutely not. Because right now, in laboratories all over the world, a quiet revolution is brewing. Scientists are refusing to concede defeat. They are rewriting the rules of engagement, developing entirely new weapons and strategies to fight back. And that's what we're exploring next.
Welcome back. We've established the terrifying scale of the superbug crisis. We're in an arms race against an enemy that evolves faster than we can innovate. But humanity is at its best when its back is against the wall. And in the fight against antimicrobitic resistance, science is unleashing an arsenal of groundbreaking new weapons that could turn the tide. Let's explore the front lines of this battle. First, the hunt for new antibiotics isn't over, it's just getting smarter. For decades, we struggled because over 99% of bacteria in the environment can't be grown in a standard petri dish, meaning their potential antibiotic-producing chemistry was hidden from us. But a breakthrough device called the iChip changed that. It allows scientists to cultivate these unculturable bacteria right in their natural soil environment. And in 2015, this technique led to the discovery of Teixobactin. What makes Teixobactin so exciting is its method of attack. Most antibiotics target bacterial proteins, which can easily mutate. Teixobactin targets lipids, fatty molecules that are essential building blocks of the bacterial cell wall. These lipids are much harder for bacteria to change, meaning resistance to Teixobactin is incredibly slow to develop. It's like trying to build a house with triangular bricks. The fundamental structure just won't allow it. And the discoveries keep coming. In early 2024, researchers announced a new class of antibiotic called zocerebalpin. This drug was specifically designed to take down one of the most dangerous superbugs on the WHO's priority list, carbapenem-resistant, CRAB. This bacterium is a nightmare in hospitals. Zocerebalpin works by jamming a crucial transport system that the bacterium uses to build its protective outer membrane. It's like blocking the main gate of a fortress, preventing it from getting the supplies it needs to maintain its walls. The fortress simply collapses. This kind of precision-guided weapon is a massive leap forward. Finding these new molecules is a monumental task, but here's where our second weapon comes in: artificial intelligence. AI is revolutionizing drug discovery. Scientists can train machine learning models on vast databases of known molecules and their properties. The AI learns what makes a molecule a good antibiotic. Then, it can be unleashed on libraries of billions of other compounds, screening them at a speed no human ever could. This is exactly how researchers at MIT discovered a powerful new antibiotic in 2020. They named it Halicin, in a nod to the sentient computer HAL 9000 from True. Halicin was a molecule previously investigated for diabetes, but the AI recognized its hidden potential as a potent bacteria killer, effective against even some of the most resistant strains. AI isn't just finding new drugs, it's helping us design them from scratch, predicting how a molecule will interact with a bacterial target before it's even synthesized. But what if we could use the bacteria's own enemies against them? Enter our third and perhaps most elegant weapon, phage therapy. Bacteriophages, or just phages, are viruses. But don't panic, these viruses only infect and kill bacteria. They are the most abundant life form on Earth and the natural predators of bacteria. The idea isn't new. Phage therapy was used in Eastern Europe for a century, but was largely forgotten in the West after the discovery of penicillin. Now it's making a dramatic comeback. Here's how it works. A phage locks on to a specific type of bacterium. injects its genetic code, and turns the bacteria into a phage-making factory. Within about 30 minutes, the cell is packed with hundreds of new phages. Then, the phages release an enzyme that bursts the bacterium open, killing it and releasing the new phage army to hunt down more of the same bacteria. It's a self-replicating, self-targeting missile. The beauty of phages is their specificity. A particular phage will only target a specific strain of bacteria, leaving our beneficial gut microbiome untouched. And best of all, as bacteria evolve to resist the phage co-evolves to overcome that resistance. It's an evolutionary arms race where we finally have an ally that can keep up. Finally, we have a tool that represents the cutting edge of biotechnology, CRISPR. We often hear about CRISPR-Cas9 as a tool for editing human genes, but its natural origin is as a bacterial immune system. And scientists have figured out how to turn that system back on the bacteria themselves. We can program a CRISPR system to act like a molecular scalpel, delivering it into a superbug and instructing it to find and cut specific genes. We could target the very genes that give the bacteria their resistance, making them vulnerable to our old antibiotics again. Or we could be even more direct and target a gene essential for the bacterium's survival, killing it outright. It's like a programmable assassin that can be tailored to any bacterial foe. The road ahead is still long. These incredible technologies need more research, clinical trials, and investment. But for the first time in decades, there is a powerful sense of hope. The combination of new antibiotic classes, AI-driven discovery, hyperspecific phage therapy, and programmable CRISPR technology represents a multi-pronged assault on antimicrobial resistance. This isn't about finding a single new magic bullet, but about building a diverse and adaptable arsenal for the future of medicine. The race to save humanity from a post-antibiotic future is on. It's a battle being fought in the unseen world of microbes by brilliant scientists around the globe. And it's a battle that depends not just on them, but on all of us, through responsible antibiotic use and support for scientific innovation. Thank you for joining us on this deep dive into one of the biggest threats and brightest hopes of modern science. If you found this fascinating and want to stay ahead of the curve on the scientific breakthroughs shaping our world, make sure to hit that subscribe button and ring the bell so you never miss an update. What do you think is the most promising approach? Let us know in the comments below. Until next time, stay curious.